theorem, but I'm telling you that this picture really says it all. Okay? So scooting down here, they talk about an area function. They give you some examples. These are great problems. I mean, don't get me wrong. You'll try them tonight. You may have tried the quick checks already. They go okay? Yeah? Okay. So, but here it is. Example 2 suggests the area function is an antiderivative. In other words, if you take the derivative, here, let me show you. Where's the statement? They do all this work, and here it is. It says, hey, suppose you have little f. That's my continuous function. I was finding the area under it. So this is our area function, right? This is what we've been saying, calling the area function. And the area function is going to be really nice. That's what the theorem says. It'll be continuous. We love continuous functions because what can we do with continuous functions? Sometimes we can take the derivative. And it turns out this area function will be differentiable. And it's easy to get the derivative. You're going to laugh when I start doing these problems using part 1. You're going to say, what? That's all there is to it? Here. The derivative of the area function is little f of x. Little f of x? What does that even mean? Let me show you some examples, and I think we'll be able to follow. Okay? Let's go down to some homework problems. Let's try, I think number 60 was one I wanted to do. Yes. I like 60. And I like 59. We'll do both of those. 59 and 60 are excellent problems to demonstrate the first fundamental theorem of calculus. So we have 59 says we want to find the derivative of the area function given by integral from 3 to x of t squared plus t plus 1 dt. Okay. So here I go. As I look at let me do a graphing calculator on this one. Say I want to graph this thing. One thing bad about the graphing calculator is I can't use the t's anymore. So I'm going to, in the y equals screen, I'm going to go ahead and type the function little f. It's t squared plus t plus 1, I know, but I'm going to pretend it says x squared plus x plus 1. Okay. And I'm going to go ahead and graph it. Cool. It's a parabola. I think I better hit zoom standard so that we're all looking at the same picture. There it is. Okay. And so now it asks me to find the derivative of this area function. Well, I have to tell you what the area function is. The area function says we want to do the definite integral from 3 to x and get some area. Okay? So maybe I need an example of what that might look like. Okay, so in this problem, f of t is t squared plus t plus 1. And I understand now from my graphing calculator that's a parabola of sorts. Now, the area function that I'm finding the derivative of is the function that measures area from 3 to x. Are you with me? By the way, this example, I claim that the derivative of this area function should always be positive. Why? Mike, you nodded your head. Why would you agree with that?
Well, because if your interval's from 3 3 to x,
Yeah.
you already hit your lowest point on the curve, so there's no way you're never not going to be increasing.
Yeah, as I move x to the right, the only way it would ever start decreasing is when your function goes below the x-axis, we get that negative thing going on. That's not going to happen in this example. You guys with me on this? So it's an increasing function. The derivative better always be positive, right? Now let's see if that's true. Well, the long way to do this problem, let me do it the long way. The long way to do this problem is the following. Take an antiderivative, right? Because we know that that bar means take an antiderivative. I showed you guys this last time. So what would the antiderivative be? Well, t squared becomes, okay, so we're going to get 1/3 t cubed plus what? 1/2 t squared plus t. Now normally we'd put plus c, but you may remember I said, hey, we don't have to do that. We're going to draw the line and we're going to put 3 and we're going to put x, right? You guys with me on this? And so then what do? Then you get, well, 1/3 x cubed plus 1/2 x squared plus x. I plug in the x. That's my, see, I'll try and show what's going on. This is my f of b, and I also need to subtract f of what? F of what? F of 3, right, because that's my f of a. F of b minus f of a. So I will subtract, and let me put some parentheses here, 1/3 of 3 cubed plus 1/2 of 3 squared plus 3. Now I mentioned this is the long way. This is the last time I want to really do it. Well, not quite. We'll do it a little bit on the homework too. Because remember what you're doing now. What am I doing to all this? This is my area function. So actually, this is kind of funny, but if you wanted to write out the area function without using the integral symbol, you could write this. It'd be some cubic thing. You could simplify that. But I don't feel like simplifying it now because what I said this fundamental theorem is about taking the derivative. Guys, we want to take the derivative of this stuff. So what do you get? What's the derivative of 1/3 x cubed? Well, 1/3, just bring that down, times what? 3x squared, right? Bing, bing. Plus 1/2, oops, 1/2, times what? What's the derivative of here? 2x. Plus 1. Minus 0, right? Why? That's a big constant. I don't know what it is, but it's a big constant. So the derivative of all this, is x squared plus x plus 1. Duh. Wait a minute. What was the original function inside the area function? T squared plus t plus 1, right? And now the derivative of that is x squared plus x plus 1. Leo, got it? So that's easy. All you have to do is replace what the book calls the dummy variable with x. And you get the derivative. But that makes sense. The derivative of the antiderivative. These are somehow inverse operations. Okay? And sure enough, this function is always positive. I actually just graphed that on the calculator. Sure. This thing is always positive. So the area function is always positive for this problem. It's always increasing. And you're going to say, there's nothing to this. And you're right. Okay? Let me go to number 60. There. This will take all of 3 seconds. We want to find the derivative of the area function given by 0 to x sine squared of t dt. So what's the answer? The answer is sine squared x. Ha! That's it. Right? That's what the fundamental theorem tells me. Well, that's nice. It's so simple. But as I said, the first fundamental, part 1 of the fundamental theorem is easy in terms of problems. Well, wait a minute. It gets a little tougher. Here, let's do one more. It's no fun when he only does the easy ones for us. How about 62? What does that ask? No, that one's... Well, let's do 61 next. Let's do 61. This is worth doing. Although timeout, I think I assigned that. I want to save it for you. Hang on, what did I assign? That's not you guys. Here's you guys. Tonight, what are we doing, guys? We're doing... Oh, yeah. Did you guys get the typos? There are typos in the answer key. Yeah, 61 is one I assigned. So, yeah, so like number 57, I noticed there was one wrong. Okay? And there's a typo in the answer key on Friday's homework. So these are right on your course schedule on Blackboard. You'll see them. But yeah, I assigned 61, so I'm going to save that for you guys. Let's look at the homework again. And let's do... I like 64. Let's do 64 next. So 64 let me put it up there again. We want to find the derivative of the area function from x to 0 of dp over p squared plus 1. Okay, so how does this work? Well, I guess I'm going to give you a little fact here that I hope makes sense, and we'll see if it does. So I'm trying to take the derivative of this area function, and if you think about it, that area function's a little different because the variable's on the bottom, right? And so I'm going to do a trick right away, see if you believe this or not. Yeah. I take the integral and I write it as 0 to x, but I put a negative sign in front. Does that make sense to you guys? The reason is, well, if you know part 2 of the fundamental theorem, again, part 2 says, how do you compute it? You do f of b minus f of a. Well, what am I doing if I switch the order? I'm doing f of a minus f of b, right? So you need a negative sign. What's 6 minus 2? Well, what's 2 minus 6? 4 and negative 4. You guys with me? So switching the order is just opposites. So I do this to start. Okay? And I'm taking, again, the derivative of this. Well, how do you take the derivative of this? This will equal negative. Well, all I do is I say I take the function that's in here. Here, let me do it one more step, slow motion. So this is minus the derivative. I could bring the negative past. And by the way, when you see this dp, this differential on top of a fraction, I want you to understand that that means the same as this. 1 over p squared plus 1 dp. Sometimes, actually most of the time, you'll see that the differential just is kind of after the function. But sometimes people get lazy, and when they have a fraction, it's kind of like this. How would you write dp as a fraction? dp over 1, right? And then you multiply them. So when people write this problem with the dp on top, I don't want you to get confused. You can kind of bring it out here, and then there's a 1 left. You guys with me? Okay. So what's the derivative of this area function? Well, I keep the negative sign that I got from switching the order, and I get 1 over x squared plus 1. 1 over x squared plus 1. You guys with me? Okay. Moving on. Let's try. Well, actually, let me give you one like that just to see, do you get this? Let's try right before it. Yeah, let's do 62. Let's do 62. Actually, let's do 63, then 62. There we go. We'll go back. 63 followed by 62. So 63, we want the derivative of this area function. X to 1, square root of t to the 4th plus 1 dt. And then 62, derivative x squared 10 dz over z squared plus 1. Yeah, 63 is better to start with, and then we'll do 62. All right, let's see if you guys got 63. I bet by now you already have it. So first step, I guess, well, I'm going to switch the order, right? This is going to be minus the derivative from 1 to x, square root of t to the 4th plus 1 dt. And so my final answer for 63 would be negative square root x to the 4th plus 1. How many people got that one? Do you guys have any questions? Taking the derivative of an area function written this way is easy. Okay, number 62. I guess first step, I'll do the same thing. But what do you notice is different about 62 that we haven't seen before?
X squared.
You have an x squared here instead of an x. And that's a problem. Okay? I'm going to write the inside like I showed you before. 1 over z squared plus 1 dz, just so that it doesn't cause any confusion. All right, now we'll see if this makes sense. I'm finding the derivative of this area function. Okay? The answer would be negative 1 over, well, let me do this. Let me do the substitution. Yeah, to see it more clearly. Let's not just give an answer. Here. Okay. We had, I just don't have enough room. I can do it here, I guess. So it's negative derivative of this thing, so I'm okay up to there. I'm trying to compute negative derivative integral 10 to x squared 1 over z squared plus 1 dz. Okay? So I'm going to do, the thing you're going to have to do for this is actually two functions put together, and you need to do a chain rule. Remember the old chain rule? Bing, bing, bong kind of stuff? Okay? So let's do this. Let's compute in the following way. I'm going to do a substitution. And this is good warm-up for next week. Actually, for this week. We're going to start, I don't know if you guys saw the schedule. Yeah, this Wednesday, I'm starting integration by substitution. I switched the order. You'll see that we're going to work on 5.5 on Wednesday, and then we'll get to 5.4. So I'm going to let u be x squared here. And if I do that, then du dx is equal to what? 2x. Now, remember, what is this big thing I just put in a rectangle? This is an area function, a of x. It's a function of x. What do you call z? What kind of variable is that? Dummy variable, right? It doesn't really mean much because we're going to get rid of it in the final answer. So a of x is here. But if I do this substitution, now the problem says, let's find negative derivative of integral from 10 to u 1 over z squared plus 1 dz. Okay? And so, notice now, this is not a function of x anymore. This is a function of what? Of u. Right? That's a function of u. So this is where I have to be really careful, and I have to remember things about the chain rule. The chain rule tells me how to find the derivative of a function of a different variable. How do I do it? Ding dong, right? So it will equal a prime of u, that's ding, but what else do I need to multiply by? Chain rule, guys. The derivative of what's inside. Remember? Dong. So what's that going to be? That's du dx. Do I have du dx? What is it? 2x. I computed that already, right? So this is the process I'm going to do here. And so I claim that our answer is equal to 1 over u squared plus 1, that's this piece, times what? Times 2x. Now, oh, and then I had a negative out front. Don't forget that negative. Negative 1 over u squared plus 1 times 2x. And if you check back at the book on this one, final answer, they would probably put the following. They would probably put the negative up top in the fraction. They'd put the 2x up top in the fraction. And then one more thing. They're not going to write u. You know what they're going to write instead? They're going to write x squared plus 1. So actually what they'd probably write is negative 2x over x to the fourth plus 1. This is the derivative. That's the answer here to number 62. Okay. So that's fundamental theorem, part 1. At least these are the problems you're going to have to do. I guess the only thing I didn't do is talk you through the proof. Let's take a peek for just a second. Why is it so simple? Why does it work? Well, look what they do. This is actually some serious mathematics going on right here. They say, hey, look at this picture. Where's the area function? The area function is in the green. All right? And they say, look, if you want to get the area function of a of x plus h, well, that's from, it depends how big h is, I guess, right? But it's from here all the way to there. And if you subtract a of x, well, that's from a to x. What you're left with is a little strip right there. And they claim these are approximately equal. Now, are they exactly equal? Why are they not exactly equal? Where's the error? Do you see the little white triangle-ish thing above? That's an error. But as h gets closer and closer to 0, the rectangle is a better approximation. We saw this last week. You guys with me? It's not bad. Some of you said, I'm going to go over the proof for 1 minute. You said, that's a 1-minute nap. Stay with me. I've only got 30 more seconds. So what do? They say these are approximately equal. They're especially equal when h gets close to 0. So let's divide by h. Dun, dun, dun! Because what's that the formula for right here? This thing called the difference quotient? That was what we called AROC. It's almost the derivative. The only thing I need to do to make it IROC, to make it the derivative, take that fraction and put what in front of it? Limit as? Yeah, and as h approaches 0, that's good for us. So they go through. They take the limit as h approaches 0 of this area function, and they say, hey, wait a minute. As h approaches 0, this limit will be close to the limit as h approaches 0 of f of x. But there are no h's here. So the answer is f of x. The thing that used to have a dummy variable, f of t, if you want the derivative, you just plug in f of x. That's part 1. That's a proof of part 1. You could read it in more detail if you want, but that should give you a flavor of what's going on. Now, they say we now have a powerful method for evaluating definite integrals. Sure beats all the geometry you're supposed to do on last night's homework. They wanted area of triangles, circles. Did you guys do it? How'd we do on the homework last night? Did you guys come in with questions? How many have questions for today? Let me ask that. No? Okay. So we can kind of keep going here. So, anyways, here's the theorem that I hinted at last night, or last week. Big F of B minus big F of A, where big F is an antiderivative. So if little f is continuous, or I said nice, and if big F is any antiderivative, then this is part 2. Notice, part 1 says, hey, you want to find the derivative of an area function, you just take the function inside, replace the dummy variable with x. Part 2 says, hey, you want to find an area, take an antiderivative and do f of the endpoints. Now, this might be a little confusing as to why it would work. It says, remember, any two antiderivatives of f differ by a constant. I have to say something about that. Remember the first antiderivative I think I gave you? Well, it was something like this. Antiderivative, this is like our favorite, of 3x squared. What do you get? This is an indefinite integral. What do we put? X cubed plus, we learned that we have to put a plus c, right? Because any of these things, if I take x cubed plus 7, x cubed plus 2, these are both antiderivatives. If I take the derivative of either one of these, you get 3x squared. You get 3x squared. Well, here's a question. Could there be something else that I take the derivative of and get 3x squared? That's a good question. Is it like, if I write x cubed plus c, here's the question that you might wonder, or I would wonder. Does every antiderivative look like this? Does every antiderivative look like that? Or could it be like, I don't know, you take the sine of x minus, you take some other function and take its derivative and you get 3x squared. Something that we're not thinking of. Well, the answer to my question, does every antiderivative look like this, is yes. But we need the mean value theorem. And the mean value theorem we skipped. That's in chapter 4. It's section 4. Where'd we go? 4.6 was the first section we skipped, right? Yeah. I skipped it for now. I thought, no, we got to get into antiderivatives first. So just so you understand, yes, every antiderivative looks like this. But we need the mean value theorem for it. Okay? So, looking back at the book, once you know that any antiderivative looks like this, a of x plus c. Why'd they use a? That seemed kind of dumb to me. And, oh, I see. Because they're saying this is going to be the area function of b. Right. Now I get it. Okay. So if you have an antiderivative, it ends up being the same as an area function. Okay? And so when you subtract, I guess the thing to know here, what is a of a? We did that already. If you replace little b with a little a, you get 0, no area. So this works. All right, it's time for examples. We got to move. I said 1 minute. That turned into 3. All right, here we go. Definite integrals. Time for these. Evaluate the following integrals using the fundamental theorem of calculus. Discuss whether your result is consistent with the figure. Yeah, 24. That's a nice problem. So let's try 24. So 24 says we want to integrate negative pi over 4 to 7 pi over 4 sine of x plus cosine of x dx. Okay? And they give me a nice picture, and they want me to look at that. Okay. So, again, the quick process is just take antiderivatives. So I need the antiderivative of the sine function and the antiderivative of the cosine function. And this drives people crazy. I had somebody on Friday at office hours tell me, I am sick of this, because you're going backwards and it drives you crazy. So write down what you think the antiderivatives are. But you know what's going to drive you crazy here is, what about the sign? Like, do I put a plus or a minus? Well, the way I do it is I always check my work. What's the derivative of the sine function? Cosine. What's the derivative of the cosine function? Negative sine, right? So you have to put a negative here to get it right. Does that make sense? The derivative of sine is cosine. The derivative of cosine is negative sine, so I have to put a negative there to get it right. And now I draw my line. And again, this is A and B. And this tells me, what the fundamental theorem says is I need to do capital F of B minus capital F of A. But this is my antiderivative, capital F of X. So the next thing I do is I fill in, let's say, capital F of B. So that would be negative cosine of 7 pi over 4 plus the sine of 7 pi over 4. And then I need to subtract F of A. And I'll write F of A in black. And see, I have these parentheses too. You have to be careful here. So I get negative cosine of negative pi over 4 plus the sine of negative pi over 4. This is crazy. So now, let me distribute the red negative. Negative cosine of 7 pi over 4. Do you guys remember the cosine of 7 pi over 4 or the sine of 7 pi over 4? Square root of 2 over 2? Yeah? I mean, picture-wise, if I'm thinking unit circle, 7 pi over 4 is almost 8 pi over 4. It's like right there, right? So yeah, square root of 2 over 2 and negative square root of 2 over 2 minus, well, it's going to become plus cosine of negative pi over 4, and it's going to become minus the sine of negative pi over 4, right? And what do you know about the cosine of negative pi over 4? Isn't that also square root of 2 over 2? Because you have the same angle going that way. You guys with me? You know what this equals? 0. Do you see it? I'll go through it in slow motion. This is negative square root of 2 over 2. This one is plus negative square root of 2 over 2. Over here, I have plus square root of 2 over 2. Oh, wait a minute. This is minus negative square root of 2 over 2, so it's going to become plus. You get 0. What a strange thing. And then they say, does this make sense when you look at the figure? Let's look at the picture one more time. Does it make sense? Why? You have this symmetry, right? You have one arch above the x-axis and you have one arch below the x-axis. Half of the area is above, half of the area is below. So the integral would be 0. Guys follow? Okay. Moving on. Evaluate these following theorems, or following integrals. Any of these you want to try? You guys pick one out, I'll do it. 28? Does that look all right? Let's try it. Let's try 28. I want to give you guys help with ones that I think you might find challenging. I don't know. Maybe this would. 1/2, 2. And we're going to do 1 minus 1 over x squared dx. Okay. Here I go. First step, I would probably take this function and rewrite it. So we're going to do the antiderivative from 1/2 to 2 of 1 minus x to the negative 2 dx. Tell you what, I'm going to type it into the calculator because I want to show you something. But you guys see if you can, from here, work it out. It might be a good exercise for you. Work with someone near you, too. See if they get the same thing. All right, let's finish up the problem here. So let's see. We have antiderivative of 1 is x, right? And then minus. And then when I do the antiderivative of x to the negative 2, I guess I would get x to the negative 1, but then I have to put a negative out front, so that becomes a plus. Does that make sense to you guys? And so where I'm evaluating it is from 1/2 to 2. So again, I got this far, and now the job is just to do my f of b minus f of a. So let me go ahead and work it out. F of b here would be, well, 2 plus 2 to the negative first power. And then I'll subtract, and I'll put some parentheses because I don't want to make a mistake when I distribute the negative. And I get 1/2 plus 1/2 to the negative first power. You guys with me? So let's see what happens here. This piece is, what's 2 to the negative first power? What's that mean? 1/2. Good. And now I'm subtracting 1/2, right? And what else am I subtracting because I distribute the negative? What's 1/2 to the negative first power? 2. You got to be kidding me. 2 plus 1/2 minus 1/2 minus 2. What's that equal? 0 again? What? All right, let's look at the picture and see if we believe that that's what the answer should be. Here's a nice picture. By the way, what's this a picture of? This is the function 1 minus 1 over x squared. And think about what we know about it. Where would we have an asymptote for this function, a vertical asymptote? X equals what? 0. So that's why we do have the picture. Now, one thing that your calculator can do, and I don't know, you probably never tried this before. Here's the graph, right? you remember trace, how you can trace? But if you hit second trace, it's the calculate menu. Look at choice 7. You see what that does? It's an antiderivative, it says, integral. Watch what happens. I'm going to press enter. It says lower limit. That means, what do you want a to equal? Well, for us, what we want a to equal 1/2. You guys with me? 1/2. Upper limit. What do we want b to equal? 2. Watch what it does. It fills in the area it's finding, and then it spits out a number. Now, what's that number? Negative 9.05 e negative. Do you guys know what e negative 12 means? Times 10 to the negative 12. So it means really big or really small? Really small number. Almost. The exact answer is 0. Remember this. Your calculator will not give you the exact answer. Why? How does it do it? It doesn't do antiderivatives. You know what it does? Well, yes. You remember all the rectangles? Left sum, right sum, midpoint sum? It does something like that. It almost does that. There's like 2 more enhancements we can make. And then that's what it does. And if you find a bunch of rectangles and add them together, you don't quite get the right answer. But it sure is close. Right? So that's nice to know. Okay. So here's from the homework last night, number 29. Yeah, so we have to find the area of this piecewise defined function. Use geometry to evaluate, sketch the graph, show the region, interpret the result. All right, I'm going to try and draw a graph for number 29. And we'll go from there. So let's see. I'm going to do it on the board to be easier. So we're going to do, as one last example, number 50 from tonight's homework. The region above the x-axis bounded by y equals 4 minus x squared. Graph the function, indicate the region in question. Okay, so my last problem here. Hey, if I sketch a graph of that, what does it look like? You guys should know that one, right? That's a parabola. Okay. So I guess my picture, y equals 4 minus x squared. And I don't need anything fancy here. It goes through, for example, 0, 4. I can see it goes through 2, 0 and negative 2, 0. And so the area they're asking me to find, again, take a look very carefully at the text. It says, find the region above the x-axis and bounded by this curve. So here's the x-axis. And so the area we're looking for is right in here. Right? So how do I represent that? This is the hard part. Writing down how we represent that area. Well, I'm going to integrate what function? This 4 minus x squared is the curve, right? So that ought to be it. But I think what I want you guys to figure out is, what are the limits of integration? What do you put above and below the integral? Can you talk to each other about that for a few seconds? That'd be worth talking about. Guys have it? What are we going to put there?
Negative 2 to 2.
-2 and 2. But again, I did some of the work for you. I told you, oh, it goes through here. They didn't tell you that, did they? So maybe I should slow down a minute. How did I know it goes through there? Well, I took the original equation, y equals 4 minus x squared, and I want to know where does it intersect the x-axis? That's what I wanted to know.
So you found the critical points, basically.
Well, x-intercepts, yes, that's what those are. Where does it intersect the x-axis? I guess what I did is I set y equal to 0. So I write down 0 is 4 minus x squared equals 4. Now you're getting plus or minus 2. And that's really all behind this. That's the hard part of this problem. It's not that hard, but you have to think of setting y equal to 0 to figure that out. Now, from here on out, can you guys get it? Okay? Probably. I think so. Antiderivative, plug in f of b minus f of a, and you guys will be set. Nice work today, guys. Homework for Wednesday is on Blackboard. There's one typo.